and a university professor of NUS. The title of his talk is Ramsey Theory in Reverse Mathematics. Let's welcome.
Thank you. I'd like to, first of all, thank the organizers for the invitation for me to be here to speak. Thank you for coming. The topic of my talk is on Ramsey theory in reverse mathematics. So I will first mention two theorems which will occupy most of the time in this talk. So in 1930, Frank Ramsey, proved the following theorem, which says that we fix any two integers n and k bigger than or equal to 1, and consider the subsets of the natural numbers of size n. So n is fixed, and take all the finite subsets of n, capital N, the natural numbers, and color them in any of the k colors. So k is bigger than or equal to 1. Then the theorem says that there is an infinite set of the set of natural numbers, all of whose n size subsets have the same color. And that infinite subset is called a homogeneous set. Yeah. And note that in the case when k is equal, n is equal to 1, we are essentially talking about the pigeonhole principle, where we decompose the set of natural numbers into k parts, and then the conclusion is that there must be an infinite subset among the k parts partition, which is one of the k parts has infinite size. So that is the simplest version of Ramsey's theorem, but in general, when n is bigger than 1, for example, it turns out to be a non-trivial matter to look for a homogeneous solution for a given coloring, k coloring of the n size subsets of the set of integers. Right. The second theorem that I want to mention is the so-called TT1. That's a tree theorem, binary tree, infinite binary tree. Here we take the full binary tree and then partition the nodes of the infinite binary tree into k parts, or similarly, we color the nodes on the binary tree in one of the k colors. Then the conclusion is that there is an infinite subtree, infinite binary subtree, all of whose nodes have the same color. Right. So we'll look at these two theorems and discuss two issues. The first is complexity. So if we have an instance, for example, of Ramsey's theorem, given n, given k, bigger or equal to 1, and how complicated is it to obtain a solution of this instance? Or in other words, how complicated is it to get an infinite homogeneous set for this coloring? So this is the first question. The second one concerns proof theoretic strength. Specifically, it means that if we are given a infinitary combinatorial principle, a combinatorial principle such as Ramsey's theorem or the tree theorem that talks about the existence of infinite objects, how much does it reveal to us about facts concerning finite tree arithmetic. By finite tree arithmetic, I mean statements or facts about numbers, right? The natural numbers. In other words, how much does the existence of an infinite object tell us about the nature of the natural numbers? So these are two things which are of interest to our investigation when we talk about what's called reverse mathematics. So to put this in the correct perspective and to make sense of these two questions, let me introduce this notion of the so-called hierarchy of arithmetical systems. These are fragments, what's called the fragments of Peano arithmetic. If you recall, by Peano arithmetic, we mean the set of axioms for arithmetic. Essentially, it consists of two parts. The first part is, we normally denote it as P minus, as you can see later. And the P minus consists of the usual arithmetic operations, laws on arithmetic operations. For example, commutativity of numbers, addition, multiplication, and distributivity, and so on and so forth. That's the P minus part. And the other part, which is very, very important in Peano arithmetic, is the axiom of on mathematical induction, which we all study in schools. So by fragments of Peano arithmetic, we mean the, well, fragments of Peano arithmetic. In particular, we restrict the strength of mathematical induction, because in general, when we talk about mathematical induction, we are talking about any statement about numbers. If it's true for 0 and true for successor, then it's all true for all the natural numbers. But when we talk about any statement, by that statement, when we formalize this notion, we are talking about any formula that we can describe in terms of the language of arithmetic. So it can be very, very complicated. But now we want to stratify that and look at so-called fragments of the arithmetic. So if you fix n bigger or equal to 1, define the following notion. I sigma n, I stands for induction. Sigma n stands for sentences in the language of arithmetic which has n alternations of quantifiers starting with existential quantifier. For example, if we are talking about sigma 1, we are saying statements of the form there exists x and not followed by something without quantifiers, but about the natural numbers, for example. If we say it's pi 1, it means that it refers to a statement that starts with a what we call a universal quantifier. So it will be for every x, and then followed by a statement that does not include any quantifiers. If we talk about sigma 2, then we are talking about sentence of the form that exists x for every y, and after that, within there we have something that about natural numbers but without quantifiers. So I sigma n says that in general, if you have n, so if n is equal to 3, for example, then we're talking about there exists x for every y, there's a z, something else, something happens. I sigma n says that induction, mathematical induction holds for statements of the form sigma 3. But equivalently, which is formulated here, it says that for every bounded set of numbers that is definable as a sigma n sentence, any such bounded set is finite. What I mean by finite is that it can be, if you take a number k, for example, bigger than 0, let's say, and then look at a subset below k, from 0 until k minus 1, then if it's sigma n definable, meaning that it has a sigma n definition, then it's finite. That means that it can be coded. Now, this sounds trivial if you look at what is called the standard numbers, but from the point of view of proof theoretic or provability, let's say, this is a non-trivial assertion. Then B sigma n says here that every bounded delta n definable set is finite. Delta n means a set which is definable in both sigma n and pi n. So in both ways it is definable. So again, this is trivially true for the normal natural numbers, but if we look at models of Peano arithmetic or fragments of Peano arithmetic, it becomes a highly non-trivial notion. Okay, P minus, as I said earlier, refers to the part of Peano arithmetic without mathematical induction, right? And then it was proved by Kirby and Paris long time ago that over the system P minus, I sigma n plus 1 strictly implies B sigma n plus 1 and strictly implies I sigma n. Sorry. Strictly implies B sigma n and all the way until B sigma 1. Okay. When we say that this strictly implies, it means that when you look at fragments of Peano arithmetic, there are models of one which are not model of the other. For example, there is a model of P minus plus B sigma n, but which is not a model of I sigma n. And there's a model of I sigma n which is not a model of B sigma n plus 1, and so on and so forth. Right? So this implication, this is a strict implication. Yeah. And that the hierarchy of arithmetic subsystems is in fact part of what is called the system of reverse mathematics. You may recall that this is Hilbert's program. Hilbert, in his 1900 address at the ICCM, proposed 23 problems. The second of his problem asked to show the consistency of arithmetic or the consistency of number theory. And to formalize his question, to understand his question properly or his problem, one has to frame it in the language of arithmetic under the notion of Peano axioms. So what Hilbert wanted to do, in fact, was to show the consistency of all of mathematics because all the paradoxes that came up. And his plan was the following. In order to show the consistency of mathematics, all of mathematics, or at least second order, so-called mathematics that talks about numbers and subsets of numbers and so on and so forth, his plan was to reduce the problem of the consistency of mathematics to the consistency of number theory. In other words, to the consistency of Peano arithmetic. But as is well known, his plan was shown to be impossible to achieve by Gödel through his incompleteness theorem. However, Hilbert's program does have a partial realization in the form of what is called reverse mathematics today. Right. So reverse mathematics, what it aims to do is to use it, is a framework to calibrate the complexity of a theorem and also the proof theoretic strength of a theorem. We want to mention a number of basic, what is called the basic subsistence of second order arithmetic. are investigated in current reverse mathematics. The base system, what is called the base system, is RCA0. RCA0 stands for recursive comprehension axiom, and consists of the following. First of all, the system includes P minus. That's the Peano axioms without mathematical induction. And secondly, has this sigma 1 induction, or I sigma 1, or equivalently, that every bounded sigma 1 definable set is finite. And thirdly, it has this closure notion, which from the viewpoint of recursion theory or computability theory, it says that if any model of RCA0 must have the property that any set of numbers, let's say capital A, if it's already in the model, then all the sets which are computable from A, all the sets B, which can be computed from A, are also in the model. And this is phrased in the following way, meaning that if X is already a set, we know that to be a set, for example, then if you have a Turing functional with oracle, so it's a Turing machine but with an oracle machine from the, if we look at it from a computer science point of view, then if that Turing functional using the set X computes a total functional, then the set being computed, call it Y, is also a set. When we say that it is a set, it means the following. We have a model. A model consists of what is called the first order part, that's the numbers, natural numbers. And then the second order part, which consists of subsets of numbers. And models of a system like that need not contain all need not contain the power set. In other words, not all the subsets of natural numbers are in there. I have to be in there. For example, if you restrict your model to sets which are recursive or computable by a Turing machine, then that's about it. Then there are only countably many such sets, second order, the so-called second order sets in that model. Anyway, so RCA is the system that is the so-called base system of reverse mathematics, consisting of the following. Then the next one is what is called WKL0. WKL0 stands for Weak-Koenig's lemma. So WKL0 is a subsystem that is stronger than RCA0. It includes RCA0 plus the axiom that says that any infinite finite branching tree must have an infinite path. Right? So that is a system that is sort of lying just above WKL0. And then after that is the system called ACA0. That's arithmetic comprehension axiom. ACA0 consists of RCA0 plus the following axiom that says that if X, capital X, is a set, then X jump is also a set. X jump, by definition, is the halting problem relative to X. For example, if X is a set of natural numbers, then X jump is the halting problem, the solution of a halting problem. So as we know, the set that we call the halting problem is a set of natural numbers that cannot be computed. Right? This is closely related to Gödel's proof of the incompleteness theorem, and is a typical example of what is called a unsolvable problem. Right? So in general, if you have a set of natural numbers, capital X, then the halting problem relative to that set X is denoted X jump. And ACA 0 says that any model of ACA 0 must have the property that if capital X is a set of numbers in the model, then its jump, we call it normally the Turing jump, is also in the model. And then we have a hierarchy of what I call to be the arithmetical subsystems. This consists of RCA 0, which is the base system, plus additional axioms. For example, RCA 0 plus B sigma n, again, RCA 0 plus the assumption that every bounded delta n set is finite. And then RCA 0 plus I sigma n, which says that every bounded sigma n definable set is finite. Right. So this gives us a system of a hierarchy of subsystems of second order arithmetic. At the top is what is called ACA 0. It's stronger than all the things that are displayed here. We have RCA 0 at the base, and then we have WKL 0, weak connects lemma on one side, and along the way you have I sigma n, which is stronger than B sigma n, and so on and so forth, and all the way to B sigma 2, and then down to I sigma 1, which is RCA 0. So this gives us a hierarchy of the subsystems that we're going to talk about in relation to Ramsey theory. Okay. So that's the system of hierarchy of subsystems. Right. So there are two questions that are of interest to us when we look at, for example, Ramsey's theorem and the tree theorem from the reverse mathematics point of view. The first question is what set existence axiom is necessary and sufficient to prove a mathematical theorem? In this case, we are talking about Ramsey's theorem and the tree theorem. The second is, well, more or less a repetition of what I said earlier. This concerns, again, proof theoretic strength. So if you have an infinite tree combinatorial principle, like Ramsey's theorem, how much does it tell us about finite tree arithmetic? Right. Now, classically, we have several examples when we consider reverse mathematics. The first one is fundamental theorem of algebra, and it is known that you can prove the fundamental theorem of algebra within the base system RCA 0, which has very weak induction requirement, just so-called sigma 1 induction. That means that all the statements that you need to use as far as mathematical induction is concerned are just the statements which are sigma 1 definable. Right. Then you have weak connects lemma, which turns out to be equivalent to Brouwer's fixed point theorem. As you know, Brouwer's fixed point theorem says that if you have a continuous function from the unit disk into itself, then there's a fixed point. Right. Then it is also known, for example, that ACA 0 is equivalent to the statement that says that every infinite set in the interval 0 to 1 has a limit point. And then there are several other examples which are not listed here, but let me just mention them because these are in combinatorics. The first one is the well-known van der Velden theorem that says that if you decompose the set of natural numbers into finitely many parts, then at least one of them will have this arithmetic progression, infinitely many of them, of a given length, for example, right? Or similarly, you color the natural numbers into k colors, then at least one of the colors will contain infinitely many arithmetic progression of a specified length. Now that theorem turns out to imply ACA 0. Right. Another example is what is known as Hyman's theorem. This is perhaps not so well known outside the combinatoric circle. Hyman's theorem says that if you again color the natural numbers into k colors, then at least one of the colors will contain an infinite set so that it is closed under finite addition. So you have an infinite set, then if you take any R numbers, x1 until xr, within that set, then the sum is also in that set. So in particular, the sum must have the same color, and so on and so forth. Now that Hyman's theorem, at this point, it's known to be stronger than ACA 0, but is it strictly stronger than ACA 0 is not known, right? But we'll come back to studying Ramsey's theorem and tree theorem for the time being, right? So we want to analyze the complexity and the proof theoretic strength, in this case in particular, what is called the inductive strength of these two theorems. And what do I mean by that? First of all, let me recall what's known. The first result that was established in relation to this was by Carl Jockers back in 1972. And he showed that if you consider n to be bigger than equal to 3 and k to be at least two colors, so then if you look at the subsets of natural numbers of size n is at least 3, and color them in any of the k colors, k is bigger than 1, then it will have a solution according to Ramsey's theorem. But according to Jockers, the existence of such a homogeneous solution, that question is equivalent to ACA 0. In other words, you require something more than what's called recursive comprehension. You require the knowledge of the halting set and x from x to x jump and so on and so on, in order to solve Ramsey's theorem for n at least 3 and k at least two colors. So then that left the question of if n bigger than or equal to 3 is so complicated, there's no computable solution, in other words, how is it compared to Ramsey's theorem when we look at pairs of numbers? So we just look at pairs of numbers, natural numbers, and color them, let's say, in two colors, blue or red. And according to Ramsey, there is an infinite homogeneous solution. How complicated is the existence of such a solution compared to when you look at triples, for example, and color them in two colors? This was solved by Slayman, Sitapan and Slayman in 1995, who showed that actually what is called RT22, Ramsey's theorem for pairs of numbers in two colors, is strictly weaker than ACA0, meaning that you can produce a model of Ramsey's theorem for pairs in which no solution computes the Turing jump, for example. No solution computes the halting set. Right. So that immediately separates what's called RT22, Ramsey's theorem for pairs, from higher power Ramsey's theorem, RT32, for example, and so on. And the question of the strength of Ramsey's theorem for pairs, since for triples, Ramsey's theorem is already equivalent to ACA0, then it clearly implies RCA0 and WKL and so on. So the question of whether Ramsey's theorem for pairs implies weak Koenig's lemma. WKL0 was remained open until it was solved by Liu Lu or Liu Jiayi in 2013, who produced a model of Ramsey's theorem for pairs in which weak Koenig's lemma is false. In other words, there is a model of Ramsey's theorem for pairs such that in that model, not every infinite finite branching tree has an infinite path. There exists an infinite finitely branching tree without a path, at least within that model. So that shows that Ramsey's theorem for pairs is not, well, relative to weak Koenig's lemma, is not particularly strong. Right. So what we have then is the following. We have a hierarchy of results relative to in relation to Ramsey's theorem. ACA0 is at the top, which is equivalent to Ramsey's theorem for triples and beyond. And then strictly below that is Ramsey's theorem for pairs, which is stronger than RCA0, the base system, but does not show WKL0. So WKL0 is on one side, and Ramsey's theorem for pairs is on the other side. Then the central question became this, meaning we know that Ramsey's theorem for pairs is weaker than ACA0, and ACA0, another way of looking at it is that it implies I sigma n for every n. That's the strength of ACA0. But now we need to pinpoint the inductive strength of Ramsey's theorem. So this remained open since 1995, but it was solved. First of all, in 1987, Jeff Hirsch showed that Ramsey's theorem for pairs must imply B sigma 2. In other words, Ramsey's theorem cannot be so weak, for pairs, cannot be so weak that it falls down to RCA0. It must be stronger than RCA0. That's the first fact that's known. And then in 2017, Slayman, Yang Ye, and myself, we show that indeed Ramsey's theorem for pairs is not strong enough to show sigma 2 induction. In other words, I sigma 2. One can produce a model. In fact, that's what was done. Produce a model of Ramsey's theorem for pairs in which sigma 2 induction fails. That means that there's a mathematical statement that involves only two quantifiers, right? Which cannot be true in the model of Ramsey's theorem for pairs. And this result was independently shown by Pate and Yokoyama just around the same time in the following year using a completely different method, right? So the conclusion that one gets here then is that while Ramsey's theorem for triples is somewhere high up there at the level of AC0, Ramsey's theorem for pairs is actually quite low down, but still stronger than the basic Ramsey's C0. Right. Now, coming to the T3 theorem, we see something actually quite similar. This was not done until later. So the first thing to note is that if you look at the tree theorem, take the infinite full binary tree and then color them in any color, and the claim is that there's an isomorphic subtree that's homogeneous. First of all, it is trivially true if you have sigma 2 induction, and it's not really difficult to do. If you just take a note on the tree, let's say you color them in K color, you take a note there, and then see whether above it there's a note above it that has the same color. If not, then it means that, for example, the first color is gone, then you're only left with K minus 1 colors. And then you do this by induction, then in finite number of steps, you conclude that there is a subtree that is isomorphic subtree that has the same color, that's infinite. So that's not difficult to do. But what was less trivial is that, in fact, this tree theorem also implies to be sigma 2. In other words, at the level of the lowest level, RCA0, it doesn't work. You have to go above it to the level of B sigma 2 in order for the tree theorem to hold. And to pinpoint the inductive strength of the tree theorem, this was done in 2020 by several colleagues, Li Wei at NUS, Wang Wei at Zhongshan University, Yang Yue at NUS, and myself. We showed that actually the tree theorem, while it is actually trivial when you're at a level of sigma 2 induction or above, but it is highly non-trivial when you get rid of that. You can still produce a model of the tree theorem without sigma 2 induction. So it is, while it is simple, it's actually deceptively simple, because when you strip sigma 2 induction away from the system, producing a tree, a homogeneous tree for a coloring becomes a non-trivial effort. Right. Now, the second part I want to talk about is what is called conservation. Now, what's conservation? Well, first of all, you take two theories called T1 and T2, or two systems, right? And you fix a collection gamma of formulas. So then you say that T1 is gamma conservative over T2 if every statement that is in gamma that T1 can prove, T2 already can prove. So in particular, if you take T1 to be a bigger system than T2, T2 is a subsystem of T1, then T1 is gamma conservative over T2 if every statement or every formula in gamma which T1 proves is already provable in T2. And this conservation is a way to measure how close T1 and T2 are. For example, if gamma is just the consists of the trivial P1 or all the axioms in P1, for example, is trivial, then T1 is always gamma conservative of the T2. But if gamma is a non-trivial collection of formulas. If you have a bigger system, T1, does it prove new theorems that T2 doesn't prove? That's the question. And the conservation notion is a way to measure the relative strength between T1 and T2. Right? So, in terms of this notion, the first result concerning conservation was proved by Pate and Yokoyama in the paper 2018, where they proved that RT22 over the base system RCA0, RT22 is what is called pi03 conservative over RCA0. What this means is that every formula that's pi03, meaning a formula of the form for every x there's a y, there's for every z, for every x there's a y, for every z, is what we call a pi3. Every formula of that form, if RCA plus RT22 proves that formula, or prove a theorem that's a phrase in that form, then that statement is already provable in RCA0. That means that RT22 does not prove new theorems which are stated or can be stated in pi03 form. So that means that as far as pi03 statements are concerned, RT22 really is no stronger than the base system RCA0. Right? Yeah. Then in 2020, 24 actually, Wang Wei, Yang and myself showed that the same thing is true of the 3 theorem. So then again, the 3 theorem seems to be a very close parallel of RT22 as far as proof theoretic strength is concerned. It does not prove new theorems of the form pi03 over RCA0. Right. So the major question, or one of the major open questions, is if you consider what we call pi11 statements, pi11 statements of the form for every capital X refers to subsets of natural numbers. So a pi11 statements of the form for every X, big X, capital X, there exists a Y, a number Y, such that something happens. So the formula after that, let's say, is quantifier free. Then the question is whether RT22 or TT1, whether any of this is pi11 conservative over B sigma 2. And let me give reasons why we are talking about B sigma 2 here. B sigma 2 is here because in both cases, RT22 and TT1, they both imply B sigma 2. So B sigma 2 has to be there. But we are interested in knowing how weak, so to speak, is RT22 or TT1 relative to this B sigma 2. In other words, that's it. We know that it does not prove new pi03 statements, but how about something much bigger, pi04, pi05, and so on, all the way up to the so-called pi11, which is second order arithmetic question. Now, I should say that if one relaxes the condition a little bit and allow what is called P sigma 1, P sigma 1 is not a statement that talks about the totality of the Ackermann function. If you know about the Ackermann function is a highly fast-growing function. It exceeds every primitive recursive function and so on and so forth. It's a recursive function, but not primitive recursive. An instance, maybe the first example, I guess, of what is known as the fast-growing function. Now, if you consider P sigma 1 then Li, Wang, Yang, and myself, we showed earlier that TT1 is in fact pi 1 conservative over this P sigma 1 plus P sigma 2. But if you take away P sigma 1, then it's not known, right? Now, coming back to some of the questions the other questions I mentioned earlier, for example, if you take Hyman's theorem, I mentioned earlier that so Hyman's theorem, just to recall, says that if you color the natural numbers into finitely many colors, k colors, let's say, then there's one particular color, an infinite set of that color, the numbers are all of that color. That infinite set has the property that every finite sum also has the same color, right? And I said that it's a theorem that implies ACA 0, but whether it's strictly stronger than ACA 0 is not known. Now, if you consider a special instance of Hyman's theorem, for example, if you just color the natural numbers in 2 colors, so every number is either blue or red, then the conclusion is that there's an infinite subset such that if you take a number x and a number y in that set, then x plus y also have the same color. Now, even that question, whether it implies B sigma 2 or stronger than B sigma 2 and so on and so forth, is unknown. So in a very strange manner, we seem to know a bit, or quite a bit, about Ramsey type questions, but there seems to be a main dividing line between 2 and 3. So for the number 2, a lot of questions remain open.
Sorry, I think the time is over, Professor.
Yes, I'm ending my talk here. Thank you very much.
Okay. One question. Since the time is over, one question, okay?
Is this Ramsey theory related to the Ramsey number? So it's the same Ramsey?
Yes. That is a Ramsey number is the finite version of Ramsey's theorem.
This is infinite version, right?
This is the infinite version.
Infinite version of the Ramsey number theory.
Yeah. Right. Yeah.
Okay, let's thank Professor Chung again. Which one?
ICCM.
ICCM
是这个吧？是不是？这不是。
纸装的是的。你现在说
我 copy 了这个。
是不是这个？这也不是。
这也不是，他给我雕的吗？我放这个。
是不是底下这个？
这个。
哦 ，OK。
这个是。
好。视图相片还是全屏模式？对，全屏模式。全屏模式。
这个好，这个就够了。
视图全屏，你好翻。
这个是？
对，你好，视图全屏你好。然后
对这个。
对，
他翻译进去。然后，
让这个工作人员。Okay. The next speaker is Professor Beifang Chen from Hong Kong University of Science and Technology. He specializes in graph theory, combinatorics, geometry, and topology. He is a tenured professor of Hong Kong University of Science and Technology and guest professor of Nankai University. The title of his talk is Foundations of Signed Graphs, Chain Groups, Matrices, and Polynomials. Let's welcome.
Thank you. Okay. I actually work on geometry and topology and also work on combinatorics.
combinatorics and graph theory. And today, my talk is basically on the graph, on the signed graphs, but related to, but this topic is related to geometry and topology in the higher dimension. And I do detailed for this one, just to set up a fundamental model, a basic model to do for the higher dimension topology, and the idea, this one. So that's why I go to the details about this, So what is the, we get several topics, but it's each one is very short. So first one, what is called, what is the graph, what is the graph, here? The graph and the sign graph. Here, I generalize the graph a little bit more, and we're now usually the graph is just a finite set of vertices and edges, and that's we also assume that. But here, each edge is connected to. Normally it's connected to two vertices. Each edge connected to two vertices, But here, well now that each edge is connected to, maybe connected to one vertex, not necessarily to connect to two vertices. It may be connected to vertices, and these two vertices may be the same. If the two vertices of the same, attached to two vertices the same, this edge is called a loop, If it's connected to distinct vertices, this is called a link, which is the ordinary edge, Now, if this edge is connected to only one vertex, this one traditionally in the history is called the half edge, but here we call it as, it's better to call it as an outer edge. So from now on, we call an edge connected to only one vertex is called an outer edge. So this one is typically, you consider system, you consider network. This network is not closed, It means that the outer edge means that it's connecting the inside into outside. And the edges, inside, bounding the two vertices. These two vertices may be the same. Then it is called, it's connected to the inside. So this outside is inside. That's the basic one. And here, it's a typical example. Say that this is a loop. And this is the outer edge. We get three outer edges right here. These are we are now the multiple edges. And in many graph theory, they said that they only allow the simple graph. Simple graph, they do not allow the loops. And they do not allow multiple edges, and of course they do not allow. And in any graph theory, they do not allow half, the outer edges, But here, we allow outer edges, and this one has its own advantage, And for sign graph, we just sign graph means that every edge we have assigned a positive sign or have a negative sign, It can be a positive sign or a negative sign. And this one is signed arbitrarily, but once it's signed, it's fixed. And any such a graph, the graph is generalized with half edge and loops and multiple edges, which the edges are given a sign, then the graph is called a sign graph. That's one slightly, So this is slightly general than the ordinary graph, But this one with the outer edge, it has a great advantage, to do many other things, So this means that with a half edge, if you consider, the linear system, or ODE, consider this one. So this is the open system. With half edge means that this is the open system. Without half edge, it is a closed system, autonomous system. All right. So now, today, we want to talk about. This is in the graph. The most important thing is about the cycles, and then get a cycle group. And so Now here, we also want to do the similarly. We want to also get the cycles. And get a cycle group. And before doing that, we need to consider. It's no battery ready. All right. And we need to give the orientation for the edges, And if the edge is positive edge is just like ordinary edge. It's just like ordinary orientation. You usually will get if like for a link, two vertices, we just from one vertex to another. So usually we'll put one arrow over there. That's the Jordan. Here we'll put two arrows. And for a loop is the positive edge. We also put the loop. It's just this area is from the vertex to itself. Okay. That's ordinary graph. And for the sine graph, okay, for a negative loop, okay, for a negative edge link, okay, usually we have the orientation is slightly different, okay. We have the we'll put two arrows pointed to the outside, like this one, or point simultaneously to the inside, okay. So this one, they are in opposite each other, okay. So that's why we did two arrows right here. And for the positive edges, and one arrow will just double another arrow. The same arrow, the two arrows are in the same direction, okay, for the positive edge. And for the negative edge, the two arrows are in opposite directions for orientation. It works now? Okay. Thank you, okay. And, okay, so that's for the loop, okay. Okay, this is okay, this is in the same direction. Okay, this is in the opposite directions. Okay, and now opposite, and the outer edge is same thing. Okay, outer edge means that the other vertex is not. There's no vertex right here. Okay. And with this one, we want to introduce okay the cycles. Okay, we want to go to the cycle group, and we do not want to okay. Okay, we just do. I need to spend a couple minutes, okay, a few seconds, okay, about why we are interested in the sine graph. Actually, the sine graph, okay, is an application, it's a semi-simple algebra, the classification of algebra by the root system, okay, the B type, okay, that's related to the, it can be described by the sine graph, okay. That's very efficiently, okay. And the social networks also use it. Originally, the sine graph comes from the social networks, okay. And the statistical mechanics, okay, spin glass, okay, and is a model and more generally for the graph, okay, the Potts model, okay, that's related to the sine graph. And inside mathematics, okay, inside the graph theory or inside the matrix theory, and the central problem, okay, in the graph theory, okay, or in the matrix theory is the classification for all matrices, okay. And the matrix, of course, this one is it's not classified, okay, of course, there's many problems, okay, it's unpaired. But the simplest one is called regular matrix. So what is called a regular matrix? Matrix is something that means that, okay, let's maybe spend 1 minute for what's called a matrix. Have you heard of matrix defined? Okay, nobody. Professor Wan knows it. You heard of matrix, right? You heard it, but you don't know what's the definition? Maybe 1 minute to what's called a matrix. It means that you take a vector space, given a vector space, no matter finite or infinite, usually, okay, we just finite dimensional, okay? We don't need an infinite dimensional. And just give a finite number of points of a given vector space. And this vector space form a matrix, okay? So now what do you mean by matrix? Just to take any man, it's form a matrix. We just take the subset, a collection of subsets of the given set of vectors. What kind of subsets we want to have? We want to have collect those subsets which are independent. We collect them. That's called a class of independent sets. These independent sets satisfy, of course, it satisfies the properties. They just abstract those properties and given for arbitrary, for abstract subset, for abstract set, you take a subclass, a class of subsets, which satisfy the properties of the subset of the finite set of a given vector space. Not mimic that property. Okay, abstract that axioms and then define the matrix. Okay, that's matrix is defined this way. Okay, and that's the one of the major, most of the matrix comes in this way. Another source of matrix comes from the graph theory. That means a given graph, you take the, you get the cycles. Okay, and the cycles you define what is our finite set. The finite set is a set of edges. So you take a class of subsets of edges, and which are called independent. Independent, what's called a subset of edges is called independent. If this set, it has a generating subgraph, and if this generating subgraph doesn't contain circle, it doesn't contain cycle, we'll call it a circle, okay? That's called a circle. And then it is called independent. And this is the class satisfied axioms, like the abstract from the linear algebra, okay? So that's the definition of the matrix. I didn't write down definition for matrix. I'm not talking about matrix in this talk, okay? And a little bit of history about this one. The classification of matrix is is the fundamental problem in the combinatorics, but no one knows how to run. Okay, the simplest one means that a matrix, representable matrix, means that it comes from the vector space, represented over the field. And if the matrix can be represented over every field, arbitrary field, okay, it means a vector space arbitrary field, any field, okay, it can be represented. This kind of a matrix is called a regular matrix. And a regular matrix means that if it can be represented, so it can be represented over Z actually. Okay, means that it's write down its matrix, and this matrix is an integral matrix. And this integral matrix, they are 0, 1, or -1. Okay, actually it should be like that. This is called every submatrix of this given matrix must be modular. Okay, I mean the determinant is equal to 0 or 1 or -1. That's the one of the lesser and sufficient condition. Okay. And another one, okay, is one, and what is the, and if you don't want to use a matrix to say that, okay, that's the symbol. Okay, now he's a professor in Princeton, and in the, I don't know that in the 70s, maybe in the 80s, okay, they classify this one. I mean, all the regular matrix can be built up from the matrix constructed from graphs, and every matrix, I just forget that every matrix has a dual matrix. Okay. So the graph, okay, a matrix from a graph, it got a matrix, and this matrix automatically has to do a matrix, and this dual matrix is called the dual graphic matrix, the co-graphic matrix. Okay, a matrix from graphs is called a graphic, and its dual matrix is called a co-graphic. So that's the two big classes of matrices. And they defined, okay, that is called a 2-sum and 3-sum. Or don't know, it's like, okay, like a topology, we get a connected sum. Okay, this one defined similar, something like that. It's called a 2-sum and a 3-sum. You don't need to know what is that. Okay, there's no time to present that. And regular matrix can be built up by taking 2-sum or 3-sum of the graphic matrix and the co-graphic matrix, and plus an actual special matrix is called R10. And this matrix has only 10 elements. Okay, there's no time to do that. It's just saying that, okay, that's the classification. And other than that one, if we want to classify the matrix, okay, other than, a little bit more than regular matrix, then it's called, okay, one, of course, that's very difficult, okay, it's impossible, okay. But what's the simplest case of non-regular matrix is called, okay, now we have a name, it's called a dyadic matrix. I mean, so the matrix which can be represented over all fields except one field, okay, one kind of field, I mean the field of characteristic 2. I mean the 1 plus 1 equal to 0, okay, that kind of field. If the matrix can be represented over all the fields except only this one, okay, exclude this one, and that one is not representable, and that's called the dyadic matrix. I think it's hopeful, okay, to have dyadic matrix can be classified, okay, with the understanding of the signed graph. And the signed graph are the building blocks, which maybe, we don't know, okay, maybe 2-sum or 3-sum or some other sums, okay, and it can be built up from this one. So if so, okay, it means that the dyadic matrix is structurally understood, okay. Will be understand, okay. So that's the story, okay, why we're interested in the okay, that's it. Okay. Well, now okay, we'll go to the chain group of the sign graph. Now, before the sign graph, we need to define the chain group. Okay. It doesn't work again. Okay, I don't know why. Okay. Anyway, okay, it doesn't matter. Okay, he's not a friend to me. Okay, I'm sorry. Okay, and the chain group. Okay. So we'll get edges. So edges, we'll talk about the oriented edges. And for all oriented edges, and we'll get 2 orientations. Every edge will get 2 opposite orientations. So for edges, we get oriented. So the edges will be, once we oriented them, okay, we get the edges are doubled. So we are any function defined on the all oriented edges and satisfy this condition. For the opposite edges, opposite oriented edges, they have opposite values in the fixed group. This group is the arbitrary abelian group. Okay. Then another one, okay, and this kind of one is form a chain. Okay, that's our chain group. Okay. Now that's called C1. Okay. the set of chains, okay, with coefficient in A, okay. And we also see C0, that's the all functions defined on the vertex set as well. Then you define the boundary operator. Here, okay, I just lazy, okay, I didn't, since we choose the coefficient in the abelian group, I should put the coefficient, say here, I just, okay, delete that one, okay, write the simple like this, okay. And for the, this for the positive edge, it's just like ordinary definition. And for the negative edge, okay, it's just a plus, okay, because this point one, okay, it's point to that one, you get a top positive sign. At point one, so both are positive sign. Here the point to the V, so this is the outer edge. O means out, okay. I mean, so we represent the outside, okay. So this point to V, so it's 1. It's point to inside, so this take a negative sign, okay, and similar, and so on and so forth. Otherwise, it's not incident, so it's 0. So define this way, we'll get a boundary operator. This one extended by linearity, we get a boundary operator. And this boundary operator in older days, okay, in algebraic topology, okay, we can define the incidence number. Okay, incidence number is just like this, okay. Now, okay, pushing this one on. Okay, it's on now. So that's incidence number, okay. For the negative loop, that will be equal to 2, okay. Another one for the link, okay, well, one that's equals 1, okay, we get the incidence number, okay. And given what's the orientation? Orientation means the selector of the oriented edges. Each edge, you only selected one orientation. So this means that only one orientation is selected, okay. We cannot select 2, okay. And the union should be the whole, okay, 1. Or to take the opposite ones, okay, that'll get a set of all orientations. That's any such a collection of oriented edges is called orientation. And you get if you fix the orientation, then you get the incidence matrix. You just take if you choose the core, okay, fix the basis, you get the incidence matrix. You get the incidence matrix, okay. And the boundary operator with the incidence number, you can define the boundary operator automatically like this, okay. And of course, the kernel is called cycle group. And in the graph theory, usually we use a different name, or just a flow, okay, just use like a flow, okay, it's called a flow group, okay. Flow group with the coefficients in the one, okay, now, okay. Now, once we defined, okay, the flow, okay, flow is just a member of the kernel of the boundary operator, okay. Now we define the so-called tension. Tension is very much like a co-chain, okay, it's very much like, but it's different from that. It's similar to that, analog to that, okay, but it's different, okay. Here's a tension is just a chain, okay. This is like here, okay, it's a chain, okay, here. I think that why, okay, I should have one slide, okay, did find, okay, okay, yeah, this, okay, it's, so this one, okay, just, okay, yeah, okay, this missing this page. And here we have a natural bilinear pairing about the chains, okay. Like for I is equal to 0, 1, okay. And for the 0, it's very much like an inner, here it's not inner product. There's no inner product right here, they are groups. And here, these are the integers, so integer valued, and this one, so multiply this one, this makes sense. Okay, so we introduce this, I think this is pretty natural, okay, the pairing, okay. It's very much, it's purpose like an inner product, okay. Then you can talk about a joint operator, okay. And that's called a joint operator. So this is like the co-boundary operator, called, okay. And the co-boundary operator for every 0 chain, okay, you get 1 chain, okay, like this, okay. Now, once you get chain, okay, you define, okay, you can also define the tension. So we get a pairing right here, okay. So pairing means that you take all chains, which is perpendicular, okay. Here is not perpendicular, yeah? So the pairing is equal to 0 for all integer valued flows. And that makes sense, okay. That pairing makes sense. So that one is equal to, that's called the tension. So this is similar to like the homomorphism, okay, like that, okay, with the inner product, okay. So tension group, just all tensions like that, okay, collect them with the coefficient A. And it has, okay, the very Okay, common properties, okay, we have, okay. You take the boundary right here, okay, you just switch this one, okay, you just pick you can put the next one, take the boundary operator, here's the co-boundary operator. Like here, I omitted the sign right here, okay. And here we should take the 1, okay, here is take the 0, okay, but we'll omit the indices, okay. And the given potential, you can find out, okay, because this you're using this property, okay, you can say this one is 1 0, so this is automatically 0. So the image is always of a tension for every potential. The potential means the column. Sometimes it's what called the column. 0 10. It's a boundary. Okay, co-boundary is always in the tension. Okay, it's a subgroup in the tension right here. Okay, and you know that this one is okay. If you take the abelian group to be the field R, okay, so these two groups, okay. They are vector space, okay. These vectors are orthogonal, okay. And the direct sum, okay, that is the whole space, whole vector space. And this space is equal to that. But if you take your A to be the ring of integers, and the rank of the two groups, the rank they are the same, okay. But okay, the quotient, okay, is not trivial, okay, it's not equal to 0, and the quotient is equal to. And for the ordinary graph, this one is equal to 1, okay. It's just counting number of bases. Number of bases in the graph theory, okay, that's called the number of trees, okay. That's counted, so this one is the number of spanning trees. In this one, okay, because this is non-regular, so for every tree, okay, for every basis, there's a counting is not a 1, it's a weight. The weight depends on the torsion, so here 1, okay. Later we're going to tell that what is that, okay. The torsion of this one, okay. That for the base, and that number is equal to, okay, and then you get the weight counting. Okay, about the matrix, okay. So we'll come to the matrix of sine graph. And for every chain, okay, we get a support. The non-zero part, okay. So for remember, it's a non-zero, okay. If the chain is non-zero, so we collect the edges of non-zero, non-vanishing edges. That's called the support of the chain. And we give an arbitrary here. We just do a little bit more general, okay. We give an arbitrary vector space over the here, okay, over the means take an arbitrary space of this chain group, okay. This is the vector space, okay. Actually, we take the real coefficient. A non-zero vector is called elementary if its support is minimal, in the sense that whenever, okay, V1 is another non-zero vector, this one is contained in the support, okay, then they're actually equal, okay. So that's called the minimal, okay. So it means the support is minimal. So those vectors, they are non-zero vectors whose support is minimal, then those vectors are called elementary, okay. And for arbitrary vector space, and you take this one, the collection of supports of elementary vectors of any vector space. This vector space should be non-zero vector, okay, non-zero vector subspace of right here. It satisfied, okay, I didn't the circuit of axioms of a matrix, okay. This one due to Tata. Then this one automatically they have a form of matrix, and this matrix is called the frame matrix of the given vector space. Now, we'll apply to the graph, sine graph case. Sine graph case, okay. Sine graph case, we have two groups. We have two vector spaces, and the flow space and tension space. And the flow space, of course, this space will generate a matrix. And that matrix is called matrix of the flow group, okay, flow vector space. And that's also called the frame matrix of the sine graph. And every such, okay, the support of a minimum, okay, of elementary vectors, elementary flows, that's called a circuit, okay. And for the tension space, it also has the matrix with T equal to this one, okay. This matrix, okay, actually, okay, it's actually the dual matrix of the frame matrix of the flow, okay, of the frame matrix of the flow space. And it's called dual matrix. So that's why sometimes we just use one matrix. This matrix is given, okay, that one is we write down the dual matrix right down this way. So this one is equal to that one, okay. And for that one, okay, so the circuit, okay, of this matrix is called the co-circuit for the frame matrix, okay. All right, okay, there's many circles, okay. One, okay, is a connected subgraph, okay. Here, okay, we'll just skip someone, okay, because we won't go to need fast, okay. So I will go to if the here we use circle because we want to distinguish it from the cycle, okay. So circle means that it is a closed path, okay. That means that it can be arranged as a closed path, okay. The edges, okay. Then that's called a circle, okay. It has a sign, okay. Just because the sign graph just multiply the sign of the edges, so that's called a sign, okay. If the sign is positive, so the circle is called a positive. Negative, so it's called a negative circle, okay. And the circuits of the framework of sine graph have 5 patterns. And this is the line, okay, with the 2 outer edges. So this is the ordinary cycle, but this is one, okay, the sign should be positive, okay. And here the total sign, okay, this one sign is negative, okay, then this negative, okay, with the negative edges, so that's negative, okay, negative 3 edges, 3 negative edges. So this is negative, this is negative, but total add up together is also positive, okay. And here this one is negative, and this one is edge. This one should be called double edges. This is 1, okay. Here is the 2 negative circles and connected by a path, okay. Just classified into 5 patterns. But originally, okay, the matrix is given is first one is introduced in the 80s by the Zaslavsky, okay, or graph theorist, okay. But who doesn't use this method, okay? Who used the 5 patterns? Just use, okay, that just we get just define the 5 patterns and check this 5 pattern of subgraphs of as edge subsets. They satisfy the check one by one the axioms of the matroid, okay. Then they call this one as a frame matroid of the signed graph. But here we do a little bit, tiny bit of algebra. And we get for every vector we get a frame matroid, and we define the flow space, and the flow space has the automatically introduced the generate matroid, and this matroid is giving exactly this matroid, okay, and is elementary, the support of elementary vectors flows, okay, it's just exactly the 5 patterns, okay. So this is a more uniform approach, okay, and an easy approach, okay, and more easy to understand. That one just check the one by one. This one, okay, write another thing, so quite boring, okay. And then with the switching, okay, someone, okay, maybe I need to skip this one, okay. It's for the for save time, okay. We don't have much time to finish, okay. This one, okay. So and the switching doesn't change, okay, the balance, okay. I mean, if the graph is called the balance, it's low negative circles. And we also have for the graph we have the bound or have the cut, and we also have we should have also define the cut, the signed graph cut. Sometimes we just call the cut, and we also have the bound. The bound is called the minimum cut. Okay, here I think we cannot. Okay, I think our time is limited. Okay, so may not. Okay, go to details for this. Okay. And here, okay, so what does the bound look like? Okay, so the bound means it's dual, but the bound and the cut, they are not intrinsic. Circuits, like flows, they are intrinsic. Like the bound cut, they are not intrinsic. It depends on ambient space. When we talk about the cut or bound, the minimal cut, we have to have a ambient space exist. We should have a signed graph exist itself, okay? We cannot talk about directly a single. We can talk about a single circuit. We can talk about a bound. Okay, what is that one itself as a bound? It should be existing. We have a big space. So that's a bound. Okay, so that's our signed graph. So the bound is like this. This is called a cut. So this is the part. Okay, this one is balance. It's complicated. Okay, and without that one, okay, just this part. Okay, we can do this one. Get rid of that one. That will be the bound. Okay, as minimum. So this is not a minimum. So that's called a cut. Okay, and the cut will have a cut chain. Okay. Okay, and to save time, okay, to get more interesting later, okay, and the bound is like this one, just only one piece like that, okay, and there's some characterizations for bound, okay, okay, and for the matrix we have the rank function, blah many things, okay. I think that it's better to skip this one, okay. Okay, and then okay, we'll talk about this is we'll talk about. The signed graph, okay, with the outer edges. So this is as a topological space. This is not a compact, okay. So when we get a compact, we have to get rid of delete all the edges. So this is the compact part. Now that's why this coincides with the ordinary notation in the graph theory. Okay. So the graph theory is just talk about always consider compact one-dimensional, simply complexities. Okay. And here, okay, we can define, okay, for the basis. Okay, the basis means that the maximum independent set. It's very much like spanning trees. Okay, if the graph is ordinary graph is connected, that's called it's just like a spanning tree. Okay, if it's not connected, like the graph, that's called a spanning forest. But here, okay, for the matrix, we just talk about the basis. Oh, use the matrix language. That's easier to understand. Okay, to talk about. And here is some technical. Maybe we just skip this one. There's no time. Okay, write down that one. Okay, talk about it takes time. Okay, how the principal basis means a special selected basis. Okay, so that we select selected basis as a principal basis. Another one we give a good result. Okay, now we get the flow structures. Okay, now we get a circuit. We get a circuit flows. Then okay, we get quickly, okay, get the one, the flow group, it is structures like this. Ordinary graph just have this part, okay. That's if the graph is ordinary graph, all edges are positive, it just have this one without this. Because this is sine graph, we have it's not, okay, if it's not, okay, balanced, then it's not equivalent to the ordinary graph. The graph, okay, this matrix is not representable over arbitrary field, okay. Over the field, okay. Over the field of characteristic 2 is not representable over there. Okay, so that one, why? Because this is a torsion 2. I said torsion 2 of the abelian group because that one we give it a contribution right here. Okay. Okay, and the most important thing that we want to talk about lower zero flows. Lower zero flows, that's the important one. That's called the flow polynomials. Okay, and for a long time. For a few decades, for a long time, okay, well, about 20 years, okay, and people worried, people in the graph theory, but not okay, topology people, they don't know this kind of one, okay. They worry that okay, what is the chromatic polynomial for sine graph? Okay, they want to have for over the modular n. They want to have this one to be the okay a polynomial, but actually it's not a polynomial. Okay, over modular n. Okay, if n is an odd number, it's a polynomial, but over even number, it's not. Okay. So the positive why is not okay, but it's best one. Okay, for me, okay, when I took this job, okay, for this one, we found that this is because the torsion plays a problem. Okay, so here, okay, we're over the arbitrary. This is for the chromatic polynomial or the flow polynomial. You take the one is over arbitrary abelian group. Okay, the number of solutions of lower zero solutions has a polynomial pattern. Okay, but for the sine graph. Flow polynomial and chromatic polynomial, the number of solutions is over the arbitrary abelian group is not a polynomial function of the order of the given abelian group or final abelian group. And if the final abelian group has no torsion 2, that means the low elements A, 2A is equal to 0. If no such a non-zero element A, which is 2 double A is equal to 0, then it is always a polynomial. But if it has okay the non-zero element, okay, then it's not okay. It's not a polynomial anymore. But it's a two-variable polynomial. We're going to say that, okay, and we'll get one. Okay, this is some number. We'll forget this one. Okay, that's technical part. We need that. So now I introduced okay a polynomial like this. Okay, that's a counting one. Okay, for sine graph. Okay, theorem. Okay, that's one. Okay, it's going to be published. Okay, that's the me. Okay, just for arbitrary. It exists a unique polynomial, okay, such that okay, the contents of lower zero flows is equal to two variables. Okay, that's the torsion of the group A, and the cardinality of the group, so it's finite group. Okay, and this one has the expansion formula like this, the flow polynomial. So, okay. And it has the recurrence relation. So, okay, I should quickly finish in this one. Okay, just 5 minutes because I lost 5 minutes. Okay, before that. Okay, let's say that. Okay, tension group will just do the same thing. Okay, yeah, just we'll quickly pass this one. Okay, and you get a tension group. Okay, the one that connects the structure of the tension group is like orthogonal to not orthogonal. It's just a dual to the flow group. Okay, and lower zero flows. Okay, as a hyperplane arrangement is just equal to related to this. Just quickly. Okay, Get this one. We get here is about chromatic polynomial. Okay, chromatic was counting the number for lower zero coloring. I mean the lower zero proper coloring or proper tensions. Okay, means that it's coboundary. Okay, it's lower zero. Okay. And this one, okay, even for chromatic polynomial, it's puzzled. Okay, they think that at the beginning they want to consider chromatic polynomial first. They found that it's not a polynomial. Okay, over the abelian group, it's not. Okay, over the one, okay, I say that they just want to know why it's not, and post this question, and nobody answered this question. But now, okay, with this kind of study, okay, that's clear. Okay, because the torsion plays an important role over there. That's why. That's the trick. Okay. All right, okay, for the tension polynomial, it's a little bit more complicated, okay. The other one is the torsion polynomial one. But this one, okay, I just recently, okay, I just carefully calculated. It's not I hope that at the beginning as well it's uniform write down this way. But this one is, sometimes this one can be negative, but I never find negative. If negative one, it should be 0, okay. That function is defined to be 0, then it matches, okay. I still don't understand why, okay, I cannot use the one nice formula to represent everything right here, okay. This is when that one, okay, this one may be, if this one is 0, the other one is equal to 1, this will be negative, okay. But for that case, it happened, okay, I do the calculation. Actually, this one should be equal to 0, okay. It's no t to negative sign, it's no that kind of a term, okay. That's the interesting part, okay. And quickly, torsion of a sine graph, okay. And torsion for a matrix, you just do the row operations, okay. You get this one, that's called a SIMIS normal form, and multiply the numbers, non-zero parts, okay, that's called the torsion of the matrix. The matrix, you get the torsion, is defined in this way, okay. For the group, that's the, it's just, this is the interpretation why this is called a torsion, okay. And torsion is if the matrix is square and non-degenerate, okay, so that's the same as a determinant, okay. And torsion for the Laplacian, okay, that one, for the graphs, the Laplacian, okay, the determinant is equal to 0, okay, you know that. But if you take a torsion of the Laplacian, for the this is also true for the ordinary graph. Ordinary graph, this one is u0 over f is always equal to 0. So 4 to the 0 is also equal to 1. So as a counting number of bases, number of Sebastian traits, okay. And for the Laplacian, if you take a determinant, you get a 0, okay. But if you take like an ordinary graph, if you take the torsion of that Laplace matrix, then that's equal to this number, okay. You don't need a determinant is equal to 0, but torsion is not 0. It's not 0. You take the SIMIS normal form and take a non-zero part and multiply them, okay. Now I'll quickly finish this one, okay. I think it's done, okay, now. And for the other matrix, we just compute the torsion, we get a nice formula, okay. And many parts I have no time to present, okay. And future work, okay, that one, okay. Work out the broken circuit theorem, okay, that's one, okay. Most of people do not understand what it is, okay. The other one is counting the coefficients of chromatic polynomial, flow polynomial, or tension polynomial, that one. And last year, okay, the field method work is awarded about the properties of the coefficients. It's satisfied the log concave property for ordinary matroid, okay. And this non-recurrent matroid, okay, we get in this one bivariant, okay, those coefficients are quite different, and we do not have this kind of property formulated, okay, one. Interpretation for the values, okay, and finding the properties for the coefficient. This one, okay, this part, nobody knows how to formulate that. I don't know how to formulate that. Application for signed networks, okay. Analysis of the signed network. This is partly done by others, okay. I already know that, okay. I have no time to check, okay, those references, okay. And generalization to higher networks, and such as simply complex, CW complex, or fiber networks. That's I want to build up a so-called fiber network. Fiber network doesn't exist. It's just in my mind, okay. I'm going to define the so-called fiber networks, okay. I'm done today. Okay, now. Okay, yes. I'm not sure if you have time for questions.
Okay. Let's thank Professor Bei Fangchen.
1 minute for the question, if you have.
Okay, one question.
Professor, as you said, the difference between signed graphs and the traditional, ordinary graphs, is that the former define a signed function. Based on that, different from the study of ordinary graphs, I would like to know what primary mathematical methods are used in the study of signed graphs.
Oh, we use here. We just mentioned that's the SIMIS normal form. That's a technique to study the matrix is not unimodular, so that's why we use it to study the torsion. Okay. And the other method we just ordinary ones. Okay. There's no mature machinery to study. We get a problem and find the problems. So there's many. Get those formulas, we have to do the deletion contraction and many dirty work to figure out that formulas. And right now, finally, in the nice formula. Okay. But someone will have to work out the details. There's no series so that you get the formula directly. Okay. But at the beginning, the formulation is very algebraic and very easy, theoretical, okay, and very organized. Okay. Not need to check case by case. Okay. From this framework. So that's why I call this as a foundation. Okay.
Thank you.
Okay. Any other questions or comments? Okay, let's thank Professor Chen again.
Thank you.
Oh, 知道。Okay. Okay, the next speaker is Dr. Junpeng Jiao from Tsinghua University. He specializes in birational geometry and singularity theory. He got his PhD from the University of Utah, and now he's a postdoc of the Yale Mathematical Sciences Center. The title of his talk is Boundings of SLC Degenerations of Polarized Log-Calabi-Yau Pairs. Let's welcome.
Thanks for the introduction. It's my great honor to give this talk. Today I will talk about the boundings of SLC degenerations of polarized log-Calabi-Yau pairs. First, let's define what is log-Calabi-Yau pairs. 这个好像不管用，要点哪一个呀？我下一页吧。Okay. So a log pair consists of a variety and a formal linear combination of irreducible divisors on it. And this we require this kx plus b to be Q Cartier. Kx is a canonical divisor. So suppose x delta is a log pair for any birational morphism y to x. We define the divisor delta y by ky plus delta y to be the pullback of kx plus delta. If E is a divisor on y, then we define the log discrepancy to be 1 minus the coefficient of delta y along E. We call x delta as LC singularity if the log discrepancy is greater or equal to 0 for all divisors over x. If you are not familiar with the log pair language, you can consider it as a smooth variety x with a simple normal crossing divisor on it, and the coefficient of this divisor is between 0 and 1. In particular, if E is a divisor over x such that the discrepancy is 0, then we call E an LC place, and its image is called an LC center of x delta. The log pair the class of all log pairs is known as a log category, and the log term seems to derive from the differential forms with logarithm singularities. Okay, and according to the minimal model program, algebraic varieties can be classified in terms of three main building blocks that generalizes Riemann surfaces of genus greater or equal to 1, and equal to 0 to a higher dimensional context. So let XB be a projective log pair with LC singularities. Then we say it is log general type if Kx plus B is big. We say it's log Calabi-Yau if it is linearly equivalent to 0. We say it's log final if Kx plus B is anti-ample. You can see here log Calabi-Yau pair is we do not need it to be simply connected or the cohomology to vanish. Because here it's in the biaxial geometry category, so we only care about its numerical properties. Okay. Now let's define for degeneration in algebraic geometry. Degeneration is taking a limit of a family of varieties, precisely giving a flat morphism of variety to a curve with orange 0. Then its fiber xt form a family of varieties over the curve. Then the fiber over 0, x0 may be thought of as a limit xt. Then we say that this family degenerates to the special fiber x0. Today we are going to talk about degenerations of log pairs, so we need to define what is families of log pairs. For families of log pairs is slightly different from families of varieties. We need to be careful with a boundary, with a divisor B. So it is an object xb to c consists of a morphism x to the curve c and an effective q divisor b, satisfying the following. The first condition is about x. It says f has to be projective, flat, or finite type, pure dimensional, with geometrically reduced fibers. The second and third is about a boundary B. The second says that every irreducible components of this B should dominate C, and all fibers of this D have pure dimensional n-1. That means we can the restriction of the divisor of every irreducible component of the divisor on every fiber is well defined. And third one is f is smooth at the generic point of x of the intersection of fiber and the support of D for every fiber. The third one says if we restrict the boundary B to every fiber, then the restriction should avoid the non-normal locus of this fiber. Okay. The reason to study degeneration, we have many reasons to study degenerations of log pairs. One of them is to study the modular space of log pairs. Modular space, roughly speaking, is a parameterizing space for the class of algebraic objects. So, for example, smooth varieties with a simple normal crossing divisor on it, it has a parameterizing space. But unluckily, this parameterizing space is not complete because the limit of smooth varieties may be unavoidably being non-smooth. So in order to compactify the modular space, we have to study the degeneration. And compactifying the modular space of Calabi-Yau varieties is a challenging problem. For a family of K3 surfaces over a punctured disk, Kolikov discovered that after a finite base change, there are degenerations with trivial canonical class. But these are usually reducible and there are infinitely many non-isomorphic ones. And the same general framework holds in higher dimensions as well. There are degenerations with trivial canonical class and SLC singularities, but usually infinitely many non-isomorphic ones. Here I said SLC. I will define what is SLC later. A general, so usually to make the modular space proper, we have to find a unique degeneration. So a general approach to obtaining unique degenerations was first explored by Alexei for abelian varieties and Hacking for plane curves. So instead of Calabi-Yau varieties, one needs to work with pairs, x and a boundary epsilon h. Here this x is a Calabi-Yau variety, h is an ample divisor, and this epsilon is between 0 and 1. For maximum generality, we consider the polarized log Calabi-Yau pairs. The polarized Calabi-Yau pairs gives a unique degeneration of all Calabi-Yau pairs. And the reason why we need to introduce SLC is short for semi-log canonical. When we consider SLC rather than just SLC is because it is discovered by Collat and Shepard Barnes that in order to compactify the modular theory of higher dimensional varieties, we need SLC pairs. SLC means that schemes that are S2 is their second condition, and whose codimension 1 points are either regular points or not. And this same is true even for curve. For example, the modular space of elliptic curve contains the degeneration of elliptic curve, which is not normal. And a polarized log Calabi-Yau pair consists of an SLC log Calabi-Yau pair XB, that is, and an effective ample integral divisor N, such that XB plus UN is SLC for any sufficiently small positive real number. And in order to make the modular space bounded, we have to add some more conditions to the polarized log Calabi-Yau pair. Fix D, a natural number, CV to be 2 positive rational number. A DCV polarized log Calabi-Yau pair is a polarized log Calabi-Yau pair XB such that the dimension is D, B equal to CD for some integral divisor D, and the volume of N to be V. Yeah. Polarized log Calabi-Yau pairs have a natural modular space. So fix a rational number epsilon and consider those polarized Calabi-Yau pairs for which XB plus is epsilon n. In the definition of polarized log Calabi-Yau pairs, we only say there exists U, but here we fix this there exists U such that XB plus UN is SLC. But here we fix this epsilon. So we have a submodular space we denote it by PCY epsilon, and it is a locally closed subset of this PCY. And this, by the definition, because Kx plus B is numerically trivial and N is ample, then this pair XB plus this XB plus epsilon N is a stable pair. Stable pair is the objects in the KSBA modular space. Roughly speaking, it is a canonical model with SLC singularities. Then the corresponding objects from an open subset, that is PCY epsilon, should embed into this the coarse modular space of stable pairs. And it is proved by Collat and Xu that there is a modular space PCY if we fix a DCV for all DCV polarized log Calabi-Yau pairs. And its irreducible components are projective. That is, there may be infinitely many irreducible components. And Professor Birka proved that this coarse modular space is actually of finite type. So it has so it is projective. It has finitely many irreducible components. Actually, Professor Birka proved the following result. He proved that all DCV polarized log-Calabi-Yau pairs are bounded. First, let's define what is bounded. We say that a set of varieties is bounded if there exists a projective morphism W to T, where T is of finite type, such that for every variety in this set, WT to X for if F is a birational map. Bounded is a very strong condition. For example, if because bounded means there is a primary tracing space. So for some property that is locally constant, then in this bounded set, in a bounded set, it has only finitely many choices. For example, let's the cohomology group, and Professor Birka proved the following: fix a dimension D, and CV be two positive rational number. Then the set of all DCV polarized log-Calabi-Yau pairs are log bounded.
What's the C? D is a dimension, and V is volume.
C is a coefficient of this B. N is an integral divisor.
In B, right? Kind of maximum.
Here, B equal to CD, and this D is an integral divisor, so C is a coefficient. And now comes to the main result. The polarized, the Moser space of polarized log-Calabi-Yau log-Calabi-Yau pairs actually gives a unique degeneration of this Calabi-Yau. And my theorem is about. And second, we assume the central fiber to have SLC singularities. And third, there is a divisor N on X such that the general fiber is a DCV polarized log-Calabi-Yau pair. Then every irreducible component of the central fiber is birationally bounded. Here we can see this divisor N is defined only on the general fiber, on the generic fiber. So and on the generic fiber, it is assumed to be ample, but we have no positivity assumption on the central fiber. So the central fiber is maybe not a polarized log-Calabi-Yau pair. And a particular case of polarized log-Calabi-Yau pairs is that of Fano pairs polarized by effective anti-pluricanonical divisors. So the following theorem is due to Professor Birka. Fix a dimension D and C be and epsilon. Then there exists a natural number n depending on D and C satisfying the following. Assume that XB is an LC pair of dimension D and X to Z is a contraction, such that the coefficient of B is in B equal to CD for an integral divisor D, and Kx plus B is anti-ample over Z. Then for any closed point on the base, there exists a Q divisor B prime, which is greater or equal to B, such that n times Kx plus B prime is linearly trivial over Z. And this xb prime is LC over a neighborhood of Z. This b prime is usually called the n complement. Roughly speaking, it says given a final contraction, we can always find a boundary to make it. We can always add a boundary to make it a log-Calabi-Yau fibration. And in particular, we can assume the coefficient of this new boundary b prime to be in a finite set. here this is because n times kx plus b prime is linearly equivalent to 0. So the coefficient of b, n times b prime should be an integral divisor. So given a final contraction, we can make it log labial. And for the to make it polarized log labial, we can add the polarization by the following. Suppose this is epsilon log canonical, then a general fiber is also epsilon log canonical final. So by the according to the Birka-BAB theorem, the general fiber is log bounded. So log bounded, the very ample index could be controlled. We take it to be m. Then this we define this n to be the following: negative m times kx plus b. So it is relatively very ample over an open subset. So it will give a polarization on the generic fiber. So with these two arguments, we have our second main theorem. Fix the dimension d and say epsilon to be two positive rational number. So let x be a quasi-projective normal variety, xb be a family of projective log pairs of dimension d over a smooth curve, and 0 is a closed point. We suppose a b equal to cd for an integral divisor, and kx plus b is anti-ample over c, so it's a final contraction. And again, the central fiber has SLC pairs, and the general fiber is epsilon log canonical. The irreducible component of the special fiber of this X0 is biaxially bounded. Note that in the two main results, we always assume the log canonical divisor of the total space, that is kx plus b, is Q Cartier. So in the first one, we assume it is rationally equivalent to 0. In the second one, we assume it is relatively anti-ample. This is because unexpected jumps of Codera dimensions happen precisely when the canonical class of the total space is not Q Cartier. The following example is well known. It is a little bit long. Let R be the embedding of P1 into P4, and T be the balance of OP14, and T be the image of embedding of P1 times P1 into P5 by the global section of O12. And CR be the projectivized cone over R, and CT be the projectivized cone over T. Then one can show that both T and CR are hyperplane sections of this CT. In particular, there is a family of surface, because they are both hyperplane sections, so we can deform T into CR. But on the other hand, we define W to be the following threefold, defined by this long equation. Then W to A1 is a family of surface. We know it's the fiber over 0 is CR, and the fiber over 1 is isomorphic to the embedding from CR to P2. And the first is a deformation from CR to P1 times P1. So we have the pathology, that is P2 and P1 times P1 have the same deformation type. This is not what we want. Such pathology happens because the log canonical class of the first one is not Q Cartier. That is Kx of the family of the first one is not Q Cartier. So we have this such pathology of deformation. Okay, and we can also notice that here the main result is every irreducible component. The main result is that every irreducible component is biaxially bounded. So it is natural to ask if we can replace this biaxial boundedness to be boundedness. But unluckily, it is not true because we have the following counterexample. That is, the degenerations of fixed varieties may not be bounded. Hacking and Prokhorov show that for any triple pair of natural numbers ABC such that a squared plus b squared plus c squared equal to 3abc, there exists a morphism x to t over a smooth curve such that kx is q car t, and the general fiber is isomorphic to P2, but the special fiber x0 is isomorphic to the weighted projective space P a squared, b squared, c squared. And this function a squared plus b squared plus c squared equal to 3abc, it is also called the Markov equation. It has infinitely many positive integer solutions. So the special fiber is not bounded, but they are all biaxially equivalent to P2. So we cannot improve the mean results from biaxial boundedness to boundedness. And also notice that in the mean theorem, it's about every irreducible component. Can we remove this thing? Can we prove that there are finitely many irreducible components? Unlikely, it is still not true, because we have the degenerations may have arbitrarily many components. The construction is a following. So suppose X B to C be a family of log pairs over a smooth curve, satisfying the assumptions, and the central fiber has more than 2 irreducible components. Because every irreducible component of the central fiber is an LC center, so its intersection is still an LC center. We can blow up its intersection, and keep blowing up, we can extract M LC places. Now this Y2C may have non-reduced fibers, but we can take a ramified cover and applying the Kalmata's trick, we can make Y2C have reduced fibers. Note that here we keep the general fiber. We keep the general fiber unchanged, but the special fiber has at least M irreducible components, and M may be arbitrarily large. So we cannot control the number of irreducible components of the central fiber of the degeneration. Okay. Now I will talk about the sketch of the proof. The main tool used in this paper are the modular space of polarized log-Abel pairs and semi-stable reductions. So because by assumption the general fiber is a DCV polarized log-Abel pair, so we can construct a modular map U to S. This U is an open subset of the curve. Sorry, here is a typo. U is an open subset of this C, of the curve. And S is a modular space of DCV polarized log-Abel pairs. So because S is a proper, the modular map will extend to a morphism C to S after a finite space change. So because we only assume the general fiber is DCV polarized Abel, so the modular map is only defined over an open subset of this C. But we can extend this modular map to make it a morphism from C to S. Then the pullback of the universal family. The DCV polarized log-Abel pair, the modular of DCV polarized log-Abel pair is a coarse modular space. So there is no universal family. But this modular comes from the Hilbert scheme. Actually, it is by taking a locally closed subvariety of the Hilbert scheme and forget its embedding into the projective space. So if we add this embedding into the projective space, we consider this as a closed subvariety in projective space. Then we can consider it as a subvariety of the Hilbert scheme, then it will have a universal family. Then the pullback of this universal family will define a new fibration, whose fibers are all DCV polarized log Calabi-Yau pairs. This new fibration we denoted by x prime, b prime, and n prime to c. This new fibration is different from the original one, x, b to c. But they have the same generic fiber because over the same generic fiber, their module space are the same. And in particular, the central fiber of the new family, of the new fibration, is log bounded because it's just a pullback of the universal family. Because this original one xb to c and the new one x prime b prime to c are both log Calabi-Yau fibrations over c, have with the same generic fiber, then they are Crepin biaxially equivalent. That is, there is a common log resolution, y to x and y to x prime, such that the pullback of kx plus b is equal to the pullback of kx prime plus b prime. So therefore, any irreducible component of this x0 on x prime is an LC place of this x prime, b prime plus x0 prime, because they are Crepin biaxially equivalent. After pulling back to y, their coefficients will be the same, will be 1. So, note that an LC center of this x prime, b prime, x0 prime is contained in the central fiber. So by subbed junction, it is also an LC center of this central fiber x0 prime, b0 prime by subbed junction. So now we show that every irreducible component x0 is an LC place. And we know that because the central fiber is bounded, it's log bounded, so its LC center is also log bounded. So now we have transformed the problem into showing that the LC places are bounded by using the LC centers are bounded. The main difficulty is because the contraction from an exception divisor to its image cannot be controlled. LC places are exception divisor, LC centers are images. We can make the images bounded, but for the exception divisor, we cannot say it is bounded because the fibration may behave wildly. Now we consider the following very good case. Suppose it's x prime b prime plus x0 prime is log smooth. Then every LC center of this is a stratum of this x prime b prime plus x0. Stratum is an irreducible component of intersection of prime divisors of this b prime plus x0 prime. So blowing up the stratum, because it is a smooth case, and the stratum is also smooth. Blowing up will extract an LC place. And this LC place is just the PR bundle over the LC center, over its image. And R is a relative dimension. For PR bundle, this is very good. If the base is bounded, then its PR bundle is obviously is biaxially bounded, because all PR bundle are biaxially trivial. But unluckily, we cannot modify the universal family to make the its pullback, to make the x prime b prime to be log smooth. Unluckily, we cannot do it. But we can use semi-stable reduction to make singularities locally toric. And for toric cases, such contraction and Professor Yao. So the description is a little bit long and contains many terms in toric varieties. But roughly speaking, it says if x prime to x is a toric biaxial morphism and P is a prime F exceptional divisor, then this exceptional divisor is biaxially equivalent to a PR bundle over its image. And to introduce semi-stable reduction, we have to define toroidal pairs first. This is a little bit long. I will make it short. Roughly speaking, a toroidal pairs is analytically looks like toric pairs. And the divisor analytically looks like a toric boundary. A toroidal morphism with toroidal morphism between projective toroidal pairs with connected fibers to be weakly semi-stable. If first, F is equidimensional. Second, all fibers of the morphism is reduced. And third, the base is non-singular. If X is also smooth, we call F is semi-stable. Semi-stable is good in our situation because of the following lemma. The following for good space change, the semi-stable is the semi-stable. This condition is kept under a good base change. So we will use this base change in the modular morphism. In 2000, Aberwolch and Caro proved that any surjective morphism of varieties with connected fibers can be made weakly semi-stable by replacing the base by a smooth alteration S prime and replacing the proper and replacing X by a modification of X prime. So moreover, they formulated a stronger conjecture that we can make it into semi-stable. And in 2019, De Presido, Liu, and Tompkins semi-stable. Let X to Z be a projective morphism between projective normal varieties with connected fibers, and D is a closed subset of X. Then there exists a proper surjective generically finite morphism of irreducible varieties A prime to Z, and the projective birational morphism X prime to this. Second, the morphism is semi-stable. So, with a semi-stable reduction, we can modify the universal family to make it semi-stable. And then suppose this C to S prime is a modular map, then its pullback is still weakly semi-stable by the previous lemma. In particular, semi-stable it is weakly semi-stable, so the X prime B prime is a toroidal pair. It has toric singularities E tau locally. Therefore, an LC place is birationally equivalent to a PR bundle over the corresponding LC center. Hence, if the LC center is bounded, then the LC places is birationally bounded. Every irreducible component of the central fiber is birationally bounded. And this result is a joint work with Chen Bingyin. It's an ongoing work. So in this theorem, fix a dimension D and say a positive rational number Ct be to non-negative rational number. Let Xb be a chaotic pair X to C to a fibration of dimension D over a smooth curve, and N be an integral divisor, 0 a closed point. So suppose Kx plus B is F nerf, B equal to CD for an integral divisor, and the general fiber is LC. The general fiber is LC, and Kxj plus Bj plus Tnj is ample. It's equal to C. That the general fiber is special, and the volume of the general fiber equal to V. Then every irreducible component of the reduction of the central fiber is birationally bounded. It is a generalization of the previous theorem. This is because first the biggest difference is that here we do not assume the central fiber to have SLC singularities. It's even maybe non-reduced. So it is about minimal. This boundness is about any fibration and the minimal fibration. That is kx plus b is f nerf. So, and although the central fiber may be non-reduced, and but it is still, the reduction is still biaxially bounded. Okay, I think that's the end of my talk.
Okay. Any questions or comments? Okay. I ask one question. Since this theorem is a generalization of the previous theorem,
Yes. Yes.
so what is the main difficulty?
Because in the previous one, first we assume this is relatively trivial, but here we generalize it to be f nerf. Trivial is obviously nerf.
Okay.
And second, this the third to the fifth condition are contained in the general fiber to be DCV polarized log labial. And we do not assume the central fiber to be reduced under SLC with SLC singularities.
Okay, so do you need to use some new techniques? Some new methods to...
Yes, the proof is similar to the we checked some we changed some detail.
Okay. Okay. Thank you. Let's thank Dr. Jiao again.
Thank you.